Hey guys, I'm gonna kind of pick up where we left off yesterday, talking about some things related to simple harmonic motion and waves. Um, the first term, and this is kind of an important one when you talk about waves and sound, is what we call resonance. Resonance has a lot to do with instruments and music, and a lot of other things. But basically, resonance. Let me put this on the full view here. Resonance is basically when something vibrates at one of its natural frequencies, okay? When you cause something to vibrate, think of like a wine glass, think of a guitar string, think of the air column and like a flute or a wind instrument of some kind. And you cause it to vibrate because of its structure and because it's what it's made out of and exactly how it's structured. It has a natural frequency that it may vibrate at, where it kind of reinforces itself and kind of creates this kind of regular recurring vibration back and forth. Okay, so when something is driven at one of these natural frequencies, that's called resonance. It's sometimes maybe useful to think of swinging on a playground swing, where to get yourself to swing and get higher and higher and higher, you have to, swing your legs forward at just the right time. If you do it at the wrong time, you're not going to get higher and higher. You wind up, kind of forcing the swing into one of its natural vibrations by kind of reinforcing it at just the right time to create that. And when things resonate, it causes this big jump in amplitude of the wave. The wave is kind of reinforcing itself. If you guys have ever kind of done that thing with a slinky where you hold it between two people and move it back and forth, and you wind up with these big waves. That happens because the wave like kind of reflects off of the wall or the other person who's holding it, and the wave's reflection winds up adding with the incoming waves, and you wind up with these big giant waves. And we'll talk more about that a little bit later, or maybe we won't, I don't know. But basically, when something vibrates at one of its natural frequencies. So I have a couple of GIFs here, or at least one of them is a GIF. The other one's supposed to be. If you look at the wine glass up at the top right here, you flick the wine glass and you see it vibrating. This is obviously way slowed down. You wouldn't be able to see this much oscillation, but this is vibrating to the point where it is vibrating past, what its structure will be able to hold, and eventually breaks. You kind of remember seeing those old things from cartoons or kind of cheesy sitcom TV shows where somebody shrieks really loud and all the glass in the room break. Doesn't really happen like that, but you actually can do that if you can create a kind of perfect pitch. The pitch of your voice can actually match the natural frequency of the wine glass, and you wind up creating these giant oscillations like that, like you see in this GIF here. These tuning forks, this GIF was supposed to show up, but it's just a picture at this point. But if you sound one of those tuning forks, it will oscillate back and forth, and this the way that it vibrates, that's the way that it resonates, and it's kind of just vibrating continually at one of its natural frequencies. Everything has a natural frequency it'll vibrate at. The pitch of a guitar string when you pluck it, a lower pitch is going to be a thicker string. The higher pitch is the thinner strings at the bottom of the guitar, and that kind of thing. Kind of a really cool example of resonance and what you might call standing waves is this example from the early 1940s of the Tacoma Narrows Bridge. It was a suspension bridge. You can play the whole video that we have in here, but I have a couple of GIFs that kind of show it to you pretty effectively here. But this bridge was a suspension bridge built in the early 1940s in Tacoma, Washington. That is Washington State. And this bridge spanned over, I forget what river, but one of the rivers over there. But it's a big suspension bridge. This is not some insignificant bridge. This is a big structure. And within a few months of it building, people noticed it starting to vibrate. The wind would whip through there and hit the face of the bridge and it would vibrate. And one particular day, the wind was coming in at just the right speed and causing it to resonate, and it vibrated in the way that you're seeing these two pictures here in the bottom left and in the top right. These are actual video of this happening. There's a car out there in the middle of the one view, and you're looking down the length of it. My favorite view is this view at the top right, where you see this whole thing just oscillating back and forth. You see one full, what you'd call standing wave there. Nothing is causing that other than the wind. And you say, how would the wind cause that? Because it's causing this vibration, and because the bridge wasn't engineered very well to kind of dampen that vibration, it just kept reinforcing itself and reinforcing itself and reinforcing itself. And you see these huge, big oscillations. And it's amazing to see that something made out of steel and concrete even has that much flexibility to create a wave in it like this. But this bridge, you'd say, is resonating. And that would mean the same thing as saying is that this bridge has a standing wave in it, much like you would see on a slinky or something of that nature. There, sorry, Mr. Hassel's was just texting me. Where you see, anything just kind of having this cool kind of standing wave pattern. And if it was getting vibrated a little bit faster, that you could create a longer standing wave where you have 1.5 or 2 full waves in there. But this is one where you have you have 1 full standing wave created in that bridge. But if you can click on that video, if you look at the actual slideshow in there, and it will show you the kind of the full story about it. It's actually pretty neat and kind of a commonly brought up, physics thing to talk about. So that was a simple case of when things resonate. And I guess one more example before I move on is it's supposed to be in nighttime mode. Stop. If you guys know either Coach Romansky or Coach Hassel's, they're gonna get it kicked that you was stuck in this middle of this video, and I can't even pause, so they're gonna keep sending silly things to each other. But imagine if you have a string with a little weight on the bottom of it, okay, and you hold that between your 2 fingers, and kind of like a little pendulum, and if you take that string and oscillate it back and forth super duper quick, it's not really, that pendulum you have in your hands isn't going to swing up a whole lot. If you also move it really, really slowly back and forth, there's not going to be a huge upswing in that pendulum either. But if you swing it back and forth, if you vibrate your fingers just a little bit at just the right rate, that pendulum that you have hanging from your fingers, it will make this huge swing up like a kid on a playground swing. So if you go too slow, it's not going to do anything. You go too fast, it's not going to do anything. If you if you go at just the right rate, then you will see this big upswing. And that's kind of how resonance works, is you were matching one of the ways that something will naturally vibrate. Okay. And this is all obviously related to waves. Okay, so a wave is a transfer of energy that transfers through matter. A wave has to go through some medium. A medium could be air, it could be water, it could be a steel beam, it could be the walls of a house. So a wave that's not an electromagnetic wave, what you'd call a mechanical wave, requires a medium. Okay, so it's like sound is always the one we always bring up. Sound requires a medium. That's why there's no sound in outer space. Any sound would have to go through radios transmitted with electromagnetic signals, which is a totally different thing. Sound cannot travel through a vacuum, and energy in mechanical waves needs some medium to travel through. And again, sound is always the kind of best instance to occur here. So a wave is a disturbance that propagates or moves from place to place, carrying energy with it. It only vibrates the medium. The medium does not transfer through it. Okay, so if you're, sitting in the lake or in the ocean and waves pass by you, those waves aren't moving you. The waves are just vibrating that water. Okay, but as a wave travels through water and just propagates the water up and down, or vibrates the water up and down as the wave travels through it. So the wave travels, the medium just vibrates. So transfers energy, not matter. If you see the wave on this picture here, see if you can count how many full waves are there. I'm counting 1, 2, 3, 4, 5, 6 full waves. Oopsies. Go back to that one. But again, each time the wave fully completes itself, that's a complete cycle, returns to back where it started from. So again, 1, 2, 3, 4, 5, 6 full waves in that picture. See if you can come up with that same number. Some people might count twice as many as that. Some other might count them up with similar near number. But make sure as you're looking at this slide, 6 full waves there. And you have 2 different types of waves. You have transverse waves. So here's our slinky. Waves in water are similar to transverse wave. They're actually a little bit different. They're what we call a surface wave. But a transverse wave, if we see it on this slinky that's being vibrated on the wall here, the medium vibrates up and down. So as this wave, if you're watching this in action, the medium would be vibrating up and down as the wave traveled side to side. So the direction of motion of the wave is perpendicular to the direction of vibration. That's what a transverse wave is. This is the classic kind of wave pattern that you would recognize. So again, the direction of motion of the wave is perpendicular to the direction of vibration. Alternatively, you also have longitudinal waves. So if you were holding that same slinky attached to a wall, and if instead of vibrating your hand up and down, you were pushing it in and out, this would be a wave in which the vibration happens as the vibration is parallel to the direction of wave travel. For the slinky, the wave would be traveling as a region of compressed springs, followed by a region of elongated springs. This is the type of wave that sound is. Sound travels, we'll consider sound to be, talking about sound moving through air, but sound travels as a region of compressed air followed by decompressed air, compression, decompression, compression, decompression. The actual term we'd use is compression and a rarefaction, but we'll get to that. So again, so in this, a full wavelength would be between the 2 compressions. And the whole slinky, if you look at each individual coil on that slinky, they would just be vibrating side to side. If you did that same thing on the previous slide and you just focused on one individual coil, each individual coil would be vibrating up and down as the wave moved from one side to the other side. So transverse and longitudinal waves. Waves in water are actually a combination, okay? They are what we call surface waves. Surface waves occur at the boundary between two mediums. Okay, so weirdly enough, anytime you see a wave in water, that there's actually a wave in air too, because air is sitting on top of that water, and the same wave pattern arises in the air above it. So any boundary between 2 mediums, you would incur this type of wave in which the medium is vibrating both up and down and side to side. If you look at the picture in the middle here, where you see this cork sitting on, some waves passing by in water, the cork is bobbing up and down, but it's also bobbing side to side. And as a full wave passes, it actually completes a full circle, as you see there. So surface waves only occur, they're called surface waves because they occur at the boundary of 2 mediums. And again, like I said, they're just a combination of transverse and longitudinal. So some wave properties, and again, you guys probably learned these before and probably know some of these, but some ways that we define waves. Okay, so the top of a wave is a crest. The bottom of a wave is a trough. It's kind of arbitrary, but that's what we call them. The displacement from its equilibrium position, from its resting position, is also called amplitude. So its amplitude is basically the height of the wave. Now it's the height of the wave, not from trough to crest, but from its equilibrium position to either the crest or either the trough. Now if you see this symbol here that's right in the center of the screen, that is the Greek letter lambda. The Greek letter lambda is indicative of wavelength. And wavelength, as you might suspect, means the length of a wave. And the space between these 2 crests here indicate a full wave. Okay, some people might say draw a wavelength, and it would only draw like half of that distance from one crest to the next trough, but that would only be half of a wavelength. A full wave, so a wavelength could be drawn from a crest to crest, from a trough to trough, or from equilibrium. So like at the very beginning here, so at the very beginning, right, we're seeing right here, it is on its way up, and then if we're moving along, some people might say, oh, right here, right in this middle part, that is your completion of your full wave. That's not accurate. That's only half of the wave. It's got to complete itself, and not until it gets back to this other point, this next point that I have in the middle of the screen here, when it's on its way back up. So this whole wave front that you see here looks like 1, 2 and a half, about almost 2 and 3/4 of a wave, but not entirely. So amplitude is the height of the wave. Wavelength is the length of the wave. All right. So what else do we have here? So again, those kind of things are indicated. Amplitude, wavelength. Wavelength is indicated with the Greek letter lambda. Distance between identical parts of consecutive waves. Amplitude is the height of the wave, period. Capital letter T would be the time for one full wave to pass, with the time for one cycle. We've already talked about period. And frequency is the reciprocal of that. It's how many full waves pass by per second, how frequently waves happen. As I said the other day, if you have like a 400 hertz sound wave, that means that 400 individual sound waves are hitting your eardrum every second. How frequently waves are coming. And frequently, if you want to express how frequently something happens, it's always got to be per time, right? And period is the reciprocal of that. So, if the frequency is 100 hertz, that means that the period is 1 over 100, so 0.01 seconds. And that would be the amount of time it takes for each individual wave to pass. Now, you also have wave speed. Wave speeds depend on the medium. They are dictated by the medium. Okay, so, you see in this equation frequency and wavelength. Like, well, the different wavelength or a different frequency, that means a different wave speed, but that's false. Okay, wave speed is only determined by the medium. And in general, the stiffer or the more rigid a medium is, the faster that wave will travel through it. So if we're talking about sound, okay, in air, sound travels around 340 meters per second, around 3 football fields per second. But if you are in water, sometimes I say, does sound travel faster in air or in water? And it's like 50-50 as to what people guess, but sound travels much faster in water than it does in air. Like, I forget the exact number, but it's something like 4,000 meters per second instead of 340 meters per second. Sound would even travel faster through like a steel beam or something like that. So even though the equation for wave speed has both frequency and wavelength in it, that just means that for a given medium, if frequency increases, wavelength reduces. As one goes up, the other has to go down. Changing the frequency does not change the wave speed. And I understand why looking at that equation might indicate to you that that is not the case, but I'm telling you, the only thing that dictates the speed of a wave is the medium, is the substance or material that the wave is traveling through. And then, so that makes that frequency and wavelength are kind of reciprocals of each other. If we then increase the frequency, the wavelength goes down. Normally, I'd be doing demonstrations with you at this point where I stretch the slinky out across the room with one person holding one end, and I go from oscillating my hand up and down slowly to oscillating my hand up and down more rapidly. And all of a sudden, you see more waves appear in the slinky, which all of a sudden more waves appear in the slinky, which means there's a smaller length in between each wave. So as you create more waves, the distance between waves reduces. So if I say, instead of going wave, 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 I go wave, 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 wave. Just like if you were timing it right now, when I went wave, 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 well, there was less time in between each wave than when I went wave, 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 which means the waves were coming more frequently and the space between them was reduced. I'll probably finish up there. Last couple things to wind down is when waves interact with each other or they interfere with each other. So if waves occupy the same space at the same time, they can add to each other, they can subtract to each other from each other. That's called interference. When they add to each other, when they line up, they are what you call in phase. You call that constructive interference. When they are out of phase, meaning you have crest line up with another wave's trough, the waves have a tendency to cancel each other out, and you have destructive interference. That's actually how noise canceling headphones work. You think that, they're noise canceling, they just block the sound from them. No, they actually create they sense a sound signal coming in, say like the sound of an airplane engine, and create the exact opposite sound wave to actually cancel it. They use the principle of destructive interference to not just block the sound, but to cancel it, which is actually pretty neat technology. So if you ever have noise canceling headphones, they do a much better job of making things quiet than just the big earmuffs things sitting over your ears. So that is how waves interact with each other. I'll talk about that a little bit more later on. There's another example. You have a pulse and a string creating constructive interference here, destructive interference on the right side. Again, you can look at the slideshow a little bit more closely if you want. I don't want to talk your ear off too much. When they're out of phase, that means you have crest lined up with trough. When they're in phase, you wind up with crest lined up with crest, trough lined up with trough. Constructive sounds like you're building something, you're building it up, and that's exactly what will happen. Destructive means you're destructing, you're burning it, you're burning it down. You are making the wave small, you're tearing a wave down, These give rise to interference patterns when you have wave fronts interacting with each other in different waves. And this next one is kind of a cool art installation that shows these interference patterns where things are crossing over, where the filled up piece of metal or whatever that's made out of crossover with the other one, and the thing actually appears to change shapes as you walk past it. Same kind of thing you see here. So this is obviously a GIF, and you see different interference patterns arising. If you take each of the black lines, and there's two sets of black lines in each of those circles to be the, say, crests of waves, you can see where you have the really dark areas be an area of constructive interference, and the really white areas be an area of destructive interference. Okay, so you can see examples of that, with art installations like this, or pieces of fencing that happen to be overlapping like that. You see those kind of patterns arising there, much like you see here. And sound works that same way, and that's how kind of, if you're an acoustical engineer and you're designing some big performance hall, the echoes of the sound interact with each other, and you don't want to be in a dead spot where like the sounds are intermittently canceling each other out and making each other bigger or whatever. So interference patterns, and I will stop there for today. Standing waves I've touched on, but I'll save that for another video. We should be ready for a concept builder or two over this stuff. Like I said, I'm moving pretty quickly, so just kind of watch these videos, knock that out, and maybe do a couple fun things as much as we can while we're distance learning. So hopefully everybody's still doing all right. Seniors, get ready to be winding down. You only got a little over a week left, so hop to it. Make sure you're staying on top of things, and I will get back to you guys later. Thanks.